So in this video, we are going to understand how we are going to construct an optimal binary search tree. And also we'll understand what are the advantages of an optimal binary search tree. And at the end, we are going to have the code which is going to help you how we are going to form the logic to create your optimal binary search tree. Now, we are going to start with a small example. Before we go with an example, we need to understand what exactly your optimal binary search tree. An optimal binary search tree is a binary search tree that minimizes the expected search cost based on given probabilities or frequencies of searching for different cases. Means what we plan to do is that we are going to create a binary search tree. You know what is the advantage of having a binary search tree? The advantage of having a binary search tree is that we can search an element very easily by using your binary search tree. So while searching the elements, we also see that that element can be searched in an effective manner, so that I can find that element with a minimum cost. So we do it with an example, as I said. So before going into that example, now we are going to understand what are or where we are going to use your optimal binary search tree, because we should know and we should understand where exactly this optimal binary search tree is to be used. Okay, so we say that we are going to use your binary search tree. Okay, now we'll see where we are going to use your optimal binary search tree. Especially your optimal binary search tree is being used in the compiler design. So we are going to use your optimal binary search tree in your compiler design. Means, see, when I compile the program, whatever the instructions and whatever the keywords which are a part of the code will be converted into a symbol table. So while forming the symbol table, so for easy process of the symbol table or for executing your program for a faster manner, we're going to search for the keywords in a faster way. So whenever I want to search for the elements in a faster way, then what we need to do is we need to construct an optimal binary search tree. Because unless we construct an optimal binary search tree, so the execution will not be fast as we expected. So we say now you're going to use your optimal binary search tree while creating the symbol table. And also your OBST is being used in database indexing also, where we are going to construct your B plus trees for faster searching the elements. So in your database table, then you're going to use your OBST tree there. And also we are going to use your OBST tree in your artificial intelligence also. Suppose I would like to identify the spam mails in your inboxes, right? Where we are going to approach the concept of an AI. Again, we are going to use the concept of OBST tree in your artificial intelligence. And also we are going to use the same OBST tree for network routing in your SDN, where we are going to have the computers around and we are going to construct a tree for these computers in a such way that we are going to construct a tree where frequently used computers are being treated as a root node, and less frequently used computers are to be treated as your left child, right child, and etc. So why we are going to construct an OBST tree for the network is to access the nodes of your network in a faster way. So that's why we are going to use your optimal binary search tree in your SDN. And also we are going to use your optimal binary search tree in your search engines also. We know the purpose of a search engine. Whenever I want to perform search in a faster way, then we are going to approach the concept of a search engine. So when I want to search a particular element in a search engine, again, the search engine is going to use your optimal binary search tree. And also your OBST is being used in your Huffman coding, where we are going to compute the data or we are going to, encode the data. Whenever I want to send the data in a faster way over the network, then we are going to use your Hoffman coding. And also, we are going to use your Hoffman coding in your spell checkers and the dictionaries also. We know what is the spell, what are the applications we have for spell checking. So for those elements also, you're going to use your optimal binary search tree. So these are the advantages where we are going to use your optimal binary search tree. Okay, and this optimal binary search tree, so we call it as an optimal binary search tree, is been using concept of dynamic programming. What it does, your optimal binary search tree is going to use a scientific technique called as dynamic programming. What we are going to do in this dynamic programming is that if I have a task, we are going to divide the task into subtasks, and we are going to find the solution of that subtask. And after finding the solution of that subtask, we are going to store the result of that subtask into an array. Whenever I encounter a task with the similar arguments or similar size, then what we do is, instead of performing or instead of calling the function again, just we are going to substitute the value of it, by which we are going to increase the efficiency of my application. So the difference between your divide and conquer and dynamic programming is that in divide and conquer, we are going to divide the subtask into, we are going to divide your task into subtask, and we are not going to store the result of the subtask when I talk about my divide and conquer. But when I talk about your dynamic programming, we are going to divide the task into subtask, and the result or the value which is coming from that subtask is being stored into a place. And whenever I encounter that, the task again, we are going to substitute the value without performing the task. We are going to just substitute the value that is going to increase the efficiency of your application. So, your OBST. So whenever I want to create your OBST, then we are going to approach the concept called as dynamic programming. So now we'll see a small example how we are going to create your optimal binary search tree for smaller elements. Okay, so when I talk about, so whenever I want to search an element, so whenever I want to search an element in your binary search tree, the complexity will be order of log n. So whenever I want to search a particular element in your binary search tree, so the complexity will be equal to order of log n. Now we'll see how we are going to construct an optimal binary search tree, and also we'll understand at the end what will be the complexity of my optimal binary search tree. Suppose I have 3 elements. Suppose now in my example, what we are going to do is, we are going to take 10 elements, like 10 is an element, 20 is an element, 30 is an element. Okay. And these are the elements now onto which I would like to construct a binary search tree. So whenever I want to construct a binary search tree, okay, so the combinations which we can have here is, because we are having only 3 elements here, on the paper or on the board, we can construct the trees. Okay, now if I construct the trees for these elements, suppose I will say, if I take my 10 as the root element, so I have 20, and then we are going to have 30. It is one form of binary search tree. You can write a tree in this manner. 10, I can have my 30, and I have my 20. It is my second form. And I can also have a tree in this manner also. I can also have a tree in this manner. And then also I can have a tree in this manner. Or also I can have a tree in this manner. So how many forms now? Just for 3 elements in my set, we are going to have 1, 2, 3, 4, 5. So we can have 5 different binary search tree can be created if you have 3 elements. Okay. Now suppose if you have n number of trees, n number of elements by onto which I would like to create your binary search tree, then we cannot we cannot draw on a paper, right? We cannot remember the combinations, and we cannot draw the combinations all at once. So we are going to have a formula. So the formula for calculating the number of possibilities of a binary search tree is 2n cn n plus 1. So this is the formula by which we are going to calculate how many possibilities we can have for this element. So if I substitute the value n here, this is equal to 20 by 4. So we are going to have 5 combinations. So how many combinations I can have now? So we have 1, 2, 3, 4, and 5 combinations. So now we are going to have 5 combinations for these elements. Now, out of these 5 different combinations of your binary search tree, now I want to identify an optimal binary search tree. So whenever I talk about an optimal binary search tree, what we need to do is we need to have the frequencies for these elements. Because unless we have the frequencies for this element, I cannot find an optimal binary search tree. Suppose I say the frequency of searching this element is a 4, the frequency of searching this element is a 2, and the frequency of searching this particular element is equal to 6. So we are going to give the numbers as 0, 1, and 2. See here. So now if I have a binary search tree in this manner, 10, 20, 30. Suppose if I have the tree here, the number of conditional statements I need for checking whether this number is there or not in the tree, it is going to have 1 conditional statement. Whenever I want to search for this element in this tree, it is going to take 2 conditional statements. And for comparing this, whether this is there or not, it is going to take 3 conditional statements. Isn't it? So if you write your binary search tree for finding these elements, whether they are there in your tree or not, it is going to take 1, 2, and as well as 3. So now what I do is, suppose if I say the frequency of my 10 is 4, it means that in my application or in my document, I want to search for this 10 element 4 times. I want to search for this 20 element in my document twice. If I say 30, it means that I want to search for this 30 element 6 times. Means we are going to create an optimal binary search tree depending only upon the frequencies. Okay. Suppose if I have this frequency, now we are going to apply these frequencies here now. I say 1 into 4, this is equal to 4. The 2 into 2 is equal to 4, and 3 into 6 is equal to 18. So 18 plus 8, it is going to give you a value called as 26. So for searching these elements, right? So for searching all these elements, so the number of operations which we are going to do is 26. If I take history, I'll take this is the number 1 operation. If I construct a tree in this way, I will take 1 conditional statement. I take 2 conditional statement. I will take 3 conditional statement. I say this is equal to 4 is equal to 4. 2 into 6 is equal to 12, and 3 into 2 will be equal to 6. So 6 plus 4 is equal to 12. 12 plus 12 is equal to 24. So the number of operations which we are going to perform on this tree, if I construct a tree in this way, this one will be equal to 24. Suppose I have a tree in this way now. Suppose if I have a tree in this way, the number of statements which I use here will be 1, this is a 2, and this is a 2. So 1, so what I do, 1 into 2 is equal to 2. Into 4, this is equal to 8, and this is equal to 6. So 8 into 2, 8 plus 2, 10, 10 plus 12. This is equal to 22. So 22 number of operations we need for finding the elements in this tree. Now, if I take this example, so I'll say 6 into 1, 4 into 2, and 2 into 3. So 6 plus 4, 6 plus 8 is 14, 14 plus 6, which one is going to, what is this value? 4, 8, 8 plus 6 is 14, 14 plus 6 is 20. So we are going to get 20 operations here. So now if you can see here now, in this tree it is 26, in this tree it is 24, in this tree it is 22, in this tree it is 20. Now if I calculate in this tree, for this tree also, so I'll say 6 into 1, 2 into 2, and 4 into 3. So this is 12 plus 4 plus 6. This is equal to 22. Now, out of these four numbers, out of these four combinations, now which tree is going to give you the minimum operations? So this tree is going to give you the minimum operations. So what we need to do now, I will say this tree now is been treated as your optimal binary search tree. Now we are doing only for my three elements. Now we are going to take an example which is going to have a bigger number. Bigger number means we are going to take four elements. We are going to understand what are the formulas we are going to use here so that we can construct the tree, and we are going to see what is the minimum cost of it, and we are going to have the code for it, and with the help of the code we are going to understand what is the cost of the optimal binary search tree. We all know what is dynamic programming is. We know that in your dynamic programming, we are going to divide your task into subtasks, and then we are going to solve those subtasks, and then we are going to save those subtasks. And whenever we need those values, we are going to substitute them instead of calling the function again. So when I talk about this dynamic programming, so this dynamic programming can be performed. Dynamic programming can be done in two ways. It can be done in two ways. But number one, I call it as memoization, and the second one, I call it as tabulation method. Means that we can implement the concept of this dynamic programming using memoization as well as your tabulation. So whenever I solve a task using your memoization, then we are going to use an approach called top-down approach. And if I use the method called tabulation, we are going to use the method called bottom-up approach. We'll see what are the features and what are the advantages we have if we are going to solve a task by using memoization as well as your tabulation. Now, whenever I talk about this memory, or if I solve the task by using your memoization, we are going to use the recursion. What we are going to use? We are going to use my recursion calls. Means we know that what is a recursion. If we are able to call a method or function within this one function, and then we call it as my recursion. So whenever I talk about this memoization technique, we are going to use your recursion calls. Yeah. And if I use your memoization, we are going to use your hash tables. We are going to use your hash tables. Plus, we are going to get the help of your arrays also. So when I use your memoization, we are going to use your hash table as well as my arrays. We know what is a hash table. Right? We can, whenever I want to search an element in a faster way, then we are going to use your hash table. Then this technique or your memoization technique is faster subproblems when we have fewer subproblems. So when we are going to use your memoization, we are going to use this memoization when we are going to have fewer subproblems. It means that if your task is there, we can have some fewer subproblems only. Then we are going to use the technique called as your memoization. And the advantage we have if I use your memoization is it is easy to understand. It is easy to understand. And then, and the main disadvantage of using this memoization technique is it can cause stack overflow. So these are the features, right? When I use my DP, by using the technique called memoization, these are the advantages, and this is one of the advantages we can find. Now, coming to your tabulation method, we can also implement the concept of my dynamic programming using tabulation method. So when I use this tabulation, then we are going to use only the iterative methods or iterative calls, or we are going to use only your iterative statements there. And instead of using the hash tables, we are going to use arrays. Which is in the form of a matrix. So we are going to utilize these arrays, and these arrays should be in the form of a matrix where it is going to contain the rows and columns also. And the main advantage of this tabulation method is it is faster. It is faster when compared to your memoization. Okay. Why it is faster? Because we are going to use my iterative statements as a part of it. Because we are going to execute things by using an iterative statement, just like that, we can say that it is faster. And it is faster for solving. It is faster for solving the subproblems. Okay. Then, and one more advantage which we are going to have here is that whenever we are going to design, whenever we are going to write the method or a function using my tabulation method, the program should be in a structured manner. It should be a structured manner. And we know that, right? We know that, right? Whenever we are going to design the program in a structured manner, right? Sometimes it can be tricky. It means that a lot of efforts are needed or understanding is needed whenever I want to write a dynamic programming concept using your tabulation method. And when I talk about my tabulation, there is no stack involved here. There is no stack. As we said in my recursion, in your memoization, we said that we are going to use the stack there. Because because we are using tabulation in the part of my tabulation, we are going to use your iterative statements. So we are not going to involve the stack. It means that execution of the topic or the execution of my program is faster when compared to your memoization if it is my tabulation method. Okay. Okay, so that's all about the different techniques we can have in your dynamic program. Now we are going to construct an optimal binary search tree by taking a small example. So we have elements like 10 is an element, 20 is an element, 30 is an element, and 40 is an element. So whenever I want to construct an optimal binary search tree, so whatever the element I would like to keep in my binary search tree should be in a sorted order. So we are going to keep these elements in a sorted order. And each and every element which is a part of your OBST tree, which we are going to create, is going to have some frequency. So the frequency of my 10 is 4, and the frequency of this 20 is 2, and the frequency of this 30 is 6, and the 40 is equal to 3. So we are taking a very old example, okay, so that we can understand this in a better way. And we are going to give these indexes starting from 0. So this is 0, 1, 2, and 3. So because we are going to have 4 elements, so what we are going to do is we are going to draw a matrix. So we are going to draw a matrix of 4 by 4 size. So we are going to have this matrix where we are going to have 16 cells. Right. So we are going to have the indexes like 0, 1, 2, 3. Then we are going to have 0, 1, 2, and 3. So now we are going to take only one element which we are going to keep in your OBST. So when we have only one element, directly what we are going to do is we are going to keep that element directly here. 0, 0 is 4. So see, the frequency of my first element is 2, 6, and 3. So I think till this point now we are able to understand how we are going to fill these elements. And remaining all elements, remaining all the boxes which we find in the matrix assumed as 0. So why we are assuming them as 0? Because while designing the logic for this optimal binary search tree, unless we are going to assume them as 0, we cannot execute the program. So we are going to assume all these boxes as 0 for now. And we are going to calculate only the boxes which are there to the upper side of my diagonal. And we are not going to consider these elements which are lower to your diagonal elements. Now, we are going to calculate this value. Now, it means this value in the sense we are going to calculate the element which is identified by 0, 1. We are going to identify the element 0, 1. 0, 1 means we are going to take 10 and 20, and we are going to create an optimal binary search tree for my 10 and 20. Because we have only elements in the tree, there is no need of implementing a formula here. We can implement the formula for these elements also, but the calculations will be big. So now what we'll do is, just because we have only elements there, we can construct them by the hand. So now whenever I want to construct an optimal binary search tree, we are going to consider the frequencies also. So the frequency of my 10 is 4, and the frequency of my 20 is 2. So according to our assumption, what we are going to do is whatever element which is having the more frequency will be at the top. So 10 will be at the top and 20 will be at the bottom. Okay. Now the frequency of my 10 is 4, and we are going to have only one operation to search that element. So this is 4 and this is into 2, because we need two operations to search my 20. So 4 into 4, 4 into 1, 4 plus 4 is equal to 8. So we are going to keep 8 here. Whenever I construct a T with this element, so the root element is 0. So we are going to keep the element called 0 here now. Now I want to construct a tree for my 1, 2. So I want to construct the elements for 1, 2. So what are the 1, 2 elements here now? 20 and 30. So we are going to construct a tree for my 20 and 30. So whenever I construct a tree, as we said earlier, the element which is having the more frequency will be at the top. So the 30 will be at the root node, and the 20 we are going to have this side. So this is 1 into 6, and this is 2 into 2. So 6 plus 4 is equal to 10. Now, when I construct this tree in this way, then what is the index of the root element now here? The index of the root element will be 2. So we are going to keep it there now. Now I want to construct, I want to keep that element in this box now. So the element which is there, which we are going to identify, this one is 2, 1, 2, 1. So now this is 2, 3. So this is 2, 3. It means now we are going to construct a tree for my 30 and 40. 30 and 40. Now, as we said that whatever the element which is having the more frequency will be at the top. So 30 will be there here, and we are going to have the 40 here now. So the frequency of this is 6. 6 into 1 plus 2 into 3. So 6 plus 3 is equal to 12. So we are going to keep 12 here. And whenever I keep this element there, so the index of this element will be treating as the root element. Now, till this point, I think now we are able to understand how we are going to fill this element. Now we are going to fill these two boxes, and at the end, we are going to fill these boxes. And after by seeing this box, now you are going to understand what will be the binary search tree, which is optimal. Okay. Now we are going to construct, we are going to calculate this value. And while calculating this value, we are going to consider the formulae, because we are going to have three elements here, because it is hard to calculate a three elemented binary circuit tree, and it's hard to calculate the minimum value of it by hand on the paper. So we are going to use a formula here by which we are going to calculate this value, and also this value. Now I want to calculate this element now. So as I said, whenever I want to calculate, so we have the formula here is T of I comma j is equal to minimum, where your R belongs to I to j, where my C of I comma R minus 1 plus, we need to erase it. So for erasing that one, I'll use an eraser. Okay. So we have, okay, then C of R plus 1 comma j plus the weight from I to j. So this is the formula which we are going to use now for calculating a binary search tree whose what you say who is treated as your optimal tree of these elements. Now, as I said earlier, now we are going to calculate 0, 2, 0, comma 2. So now I'll say I want to calculate 0, 2. So if I want to calculate 0, 2, so the value of my R will be equal to 0, the value of my R will be equal to 1, and the value of my R will be equal to 2. So out of them, we are going to find the minimum, and that minimum value which we are going to get, we are going to keep in this box. Now first we'll calculate this weight of I to j. I is 0 to j. So what we are going to do, we are going to add this frequency. 0, 1, 2. So this 0, 1, 2. So this is equal to 12. So this value is not going to change for this iteration. So we can have this value is my 12. Okay. Now when my R is equal to 0, we are going to see. So I is equal to 0. 0 minus 1 is equal to minus 1 plus R plus 1, where my R is equal to 0. If my R is equal to 0, so R 0 plus 1 is equal to 1. And what is the value of my j? 2 plus the value 12. So this is 0, comma minus 1 is not going to exist in the matrix. So whenever this element is not going to exist in the matrix, it is been assumed as 0 plus. Now we are going to take the value from the matrix of 1, comma 2. Now we go to the matrix and we'll see 1, comma 2. So the value which is there in the matrix of 1, comma 2 is 10. What we are going to do, we are going to take that value and we are going to add the value called 12. So if I add these two elements, so this is equal to 22. So now we are going to get an element called as 22 there. Now I'll say, now we are going to take R is equal to 1. If I take R is equal to 1, so the value of my I is equal to 0, and 1 minus 1 is going to give you 0, plus R is equal to 1. So 1 plus 1 is equal to 2, and the value of my J is also equal to 2 plus 12. So this is equal to 0, 0. So if I go to my 0, 0, this is 4. So we are going to substitute that value 4 here plus 2, 2. And the value of my 2, 2 is equal to 6 plus 12 is equal to 22. Okay. Now we are going to calculate when the value of my R is equal to 2. So if I calculate my R is equal to 2, so this is equal to 0, 1 plus this is equal to 3, 2 plus 12. This is going to become, so if I say 0, 1, so the value of my 0, 1 is equal to 8 plus your 3, 2 is not going to exist because this is not going to exist. It is going to be treated as 0 plus 12 and this is going to give you 20. So we are going to find the minimum of these three numbers. And the minimum of these three numbers is 20. And we are going to get the 20 when the value of my R value is equal to 2. So what we are going to do? Now we are going to fill this one, 20, and the value of my R is equal to 2. In the same way, we are going to calculate this value. And this value is equal to 1, 3. Now we go there. Now we are going to calculate for 1, 3. If I want to calculate for 1, 3, the R value will be equal to 1, R value will be equal to 2, and the R value will be equal to 3. Okay. Now, so if you substitute the value of my R in the formula, this is going to become 1, 0 plus 2, 3, and the weight which we are going to get. So I say 1, 2, 3. So what we are going to do? We are going to add 1, 2, 3. So 6 plus 2 plus 3, it is equal to 11. So we are going to keep this as 11. Because we know that 1, 0 is not going to exist. So we are going to assume it as 0 plus 3. And the value of my 2, 3 is 12. So we are going to add 12 plus 11. This is going to give you 23. So if the value of my R is equal to 1 and if you are going to substitute this number in your formula, this value we are going to get is 23. Now we are going to say R is equal to 2. And if this R is equal to 2, we are going to get 1, 1. Then we are going to have 3, 3 plus the value 11. 1, 1 value is equal to 2 plus 3, 3 value is equal to 3 plus 11. Altogether, this number is going to give you 16. So if the value of my R is equal to 2, the value which we are going to get if I substitute them here is equal to 16. Now we are going to do the same thing when my R is equal to 3. R is equal to 3, it means that now we are going to assume the root element as my third element. If you are saying R is equal to 2, it means that we are assuming that the second element or my index of 2 element is been treated as a root element. If you say R is equal to 1, it means that this element is been treated as a root element. So if the first element of my 0, 1, 2, 3 elements are, if my first element is the root element, the value or the frequencies we get if I create a binary search tree is 23, and if I do it with my R is equal to 2, we are going to get 16. Now we are going to say for R is equal to 3. If my R is equal to 3, this is 1, 2 plus 4, 3 plus 11. And 1, 2 value is equal to 10 from that matrix, and 4, 3 is not going to exist. If it is not going to exist, then we are going to keep it as 0 plus 11. So this is going to give you 21. So now what we need to do now, we need to take the minimum element of these three elements. So the minimum of these three elements is 16. And we are going to get 16 when the R value is equal to 2. So what I do now, we are going to fill this 16 when your R value is equal to 2. Okay. Now we need to calculate this this box now. It means it is going to get 0, 3. So now we are going to calculate for C of 0, 3. So if I say 0, 3, then the value of my R will be equal to 0. The R value of R is equal to 1. The value R is equal to 2. And then R is equal to 3. And what is the formula we are having here now? Here the formula which we are going to have here is that we are going to find the minimum where my R is going to belonging to from I to J, where my cost of I comma R minus 1 plus cost of R plus 1 comma J plus weight of I to J. So this is the formula which we are going to going to send now. Now we are going to see what is the value of when my R is equal to 0. Again, if I say R is equal to 0, it means that we are assuming that the 0th element of my array is treated as your root index, root value. So if I substitute them in the formula, this is equal to 0 comma minus 1 plus 1 comma 3 plus 15. If we are going to add them, it is equal to 15. So 0 comma minus 1 is not going to exist. So this is equal to 0 plus 16 plus 15. This is going to give you 31. So when my root element is equal to 0, then we are going to get the value called as 31. Now we'll see what is the value if it is R is equal to 1. If my R is equal to 1, this is 0 comma 0 plus 2 comma 3. So 0 comma 0 is equal to 4 plus 2 comma 3 is equal to 12 plus 15. This is going to give you 31 again. Now we are going to calculate when R is equal to 2. If R is equal to 2, then 0 comma 1 plus 3 comma 3 plus 15. 0 comma 1 is equal to 8. 3 comma 3 is going to become 3 plus 15. This is going to give you 26. Now when R is equal to 3, it means that that element indexed by 3 is treated as my root element. So if it is treated as a root element, then what is the values we are going to get? 0 comma 2 plus 4 comma 3 plus 15. So this is 20 plus 15, because 4 comma 3 doesn't exist, it is 0. So we are going to get it as 35. Out of these 4 elements, which is the minimum one now, and when we are going to get this minimum value, we are going to get the minimum value when my k is equal to k, where my R is equal to 2. So we are going to take this element. So we are going to take this element 26, and we are going to fill this box with my 26, and we are going to say this 2 is the value or the root element for my k. Now we know what is the root element now. So if you go there, now we are going to say the root element. So the root element is my second element is my, it means that the root element is my 30. Now what is the element which we are going to have to my left side, because we are going to follow the standards of my binary search tree. And now, after getting this 30, now we need to find which element is having the more frequency. So we are going to have my 10, and then we are going to have my 20 here. So this is the optimal binary search tree for those elements of that frequency. This is how we are going to construct a binary search tree by taking the R value. Now we are going to understand what will be the code of it. We'll see what will be the code, and we'll understand how we are going to construct the logic for it so that we can execute the program, and we'll have confidence how we are going to convert this concept into the code so that we should be habituated to write the code. So now we are going to understand the program which is used for finding the optimal binary search tree value. So by which we can construct an optimal binary search tree very easily. So now, according to my earlier example, so what we were doing is we are going to take this. What do you say? We are going to take the values. We are going to have the frequencies like 4, 2, 6, 3. Okay, and then we are going to have the values of it like 10, 20, 30, and 40. So now we are going to write a program, right, by which we are going to calculate the value of my OBST. Now we had the values like 10 was a value, 20 was a value, 30 was a value, and 40 was a value, right? So now my intent, my code is to write, my code is to create an OBST tree for these values of these frequencies. So we are going to calculate the size n. So by using this instruction, we are going to calculate the number of elements onto which we are going to create your binary search tree. And then we are going to develop a program or develop a function, the name called optimal BST, where we are going to send this frequency and this n value as an argument of it. So we are going to call this function, and what this function is going to do is this function is going to return a value, right, which is the topmost value, right? So in my example, right, we got the element, we got the value called as 26. So that 26 value we're going to get here as an output of my program. So now we'll see what are the parts we are going to have in this program. We'll see. So we have like we have the programs. So as a part of the program, we are going to write a function here, right? So the name of the function is sum, which is going to take frequency as the argument, and then it is going to take the value of I as the second argument and j as your third argument. Now we can understand what is the use of I and j. So we can say that this I and j will be the starting value as well as the ending value of it, right? So we know what is the value of my I. So because we'll say whenever I want to construct a tree there, suppose I say 0 and 1. Sometimes we are going to construct a tree for 0 and 2. So in this case, the value of I will be 0 and the value of my I will be, my j will be equal to 1. So this is going to specify from where to where we are going to construct the tree. So we are going to construct a tree for two elements, like sometimes we are going to construct the tree for 10, 20. We are going to construct the tree for 10, 20, 30. And then we are going to construct the tree for 10, 20, 30, and 40. So when we are going to construct trees for these numbers, we are not going to take these values, but we are going to take the frequencies of it. So now if you take this example, suppose in this case, the frequency of my 10 is 4 and the frequency of my 20 is 2. And the frequency of my 4 to 6 and then 4 to 6, 3. What this function is going to do is this, at this point of time, this is going to return a value 6. At this point of time, it is going to return a value of 12. And at this point of time, it is going to return a value of 4 plus 2, 6, 6, 6, 12, 12 plus 3 is equal to 15. So this value, so it means that this function is being called for 3 times. When the values of 2, it is going to return a value 6, and when the value is 3, it is going to return the value 12, and then when we are going to have 4 values, then it is going to return a value 15. So this function, right, is being called while building your optimal binary search tree. So now we'll see how and what is going to happen when I call this function. Okay. So now we are going to call the method called optimal BST. So now we can see the function there, which is going to take the frequencies, and along with the frequencies is going to take the value of my n as an argument, right? So now we'll see what this function is going to do. What we are going to do as a part of your function, we are going to have a matrix of n by n. As I said, we are going to create my 4 by 4 matrix there, because we are going to have the elements like 0, 1, 2, 3, 4. So we had this matrix earlier. And now what I'm doing at this point of time, we are going to fill the diagonals here now. So as I said, we are going to have a matrix in this way, where we are going to have 16 cells are there. So what I do at that part, right, isn't it? We are going to fill your diagonal elements. So your diagonal elements are 4, 2, 6, and 3. Okay. Now we are going to fill this diagonal element at this point of time. Now, after filling these elements, now we are going to have a loop here. So when I have a loop here, we are going to start that loop from 2 less than or equal to n l plus plus. Now, when I say L, where my L is will indicate that it is the size or the number of elements which I would like to include into your binary search tree. So at this point of time, we are going to say 2. It means that we are going to include 2 elements into binary search tree. And then we are going to increment the value for the next iteration. And if I increment the value of that L, it means that L is going to become 3. It means we are going to include 3 elements into that binary search tree. And at the last, we are going to include all 4 elements which I would like to construct a binary search tree. So this statement is going to say how many elements of my binary search tree has to be included into your optimal binary search tree. Okay, now we are going to have this loop now. This loop says the what you say for the first item, we are going to say we are going to perform this on the 0th row. Then I'll increment the value of my I. Then I will calculate the value here. Now we are going to calculate this item. After calculating this item, then we need to calculate this item, and then we are going to calculate this item. So we are going to have this I, we are going to have this I for the values of 0, 1, 2 in this example. So we are going to calculate this element, we are going to calculate this element, and then we are going to calculate this element. So this I is going to calculate the row value. That this J is going to calculate, suppose now if I take this example of the cell, so I need to calculate 0, 1, then we need to calculate my 1, 2, and then we are going to calculate my 2, 3. So what my J is going to do, this J is going to generate 1, 2, 3, and this I is going to generate 0, 1, 2. So these are the values, right, which we are going to generate for every iteration, not at once, but these values are being generated iteration by iteration. Then, and for these values, so because before evaluating these numbers, so what I do is by default, we are going to initialize them for 999, because see, because for developing an easy logic, right, what we are going to do is we are going to store the value called 999, so that it will be very much easy for us to develop the logic for us. Now we are going to have one more loop here called R loop. Now, in my example, right, when I was talking regarding my example, what I said is we are going to take a variable. We are going to take a variable called as R, right? What that R is going to do? That R is going to say when if I say R is equal to 0, if I say R is equal to 0, it means that the 0th element of my array will be treated as the root element. And then I'll be saying R is equal to 1. It means that this 1 is going to become the root element of the tree, and we are going to perform the operations with the by assuming these values as my root elements, right? Now in the loop, what we are going to do is we are going to calculate the left cost, okay, and then we are going to calculate the right cost, okay, and then we are going to calculate, we are going to add left cost, right cost, and then we are going to call the sum function. As I said earlier, we are going to have a value, we are going to have a method called sum, where we are going to send the frequency as the first argument and the value of my I, the this is called as the row, and this is called as my column, right? So we are going to send these three things as an argument, because for the first time we are going to take only two elements, for the second time we are going to take three elements, and then we are going to take four elements. As I said, we are going to add the frequencies here, and then we are going to add my left cost, and then we are going to add my right cost, and all of them we are going to calculate into my total cost, and we'll see whether my total cost is less than of my cost of I of j, because we are assuming that beginning of the loop my cost of ij was 999. So we are going to compare this value with this number. So by this statement, what we are going to do is we are going to calculate the least cost. What we are doing now, we are going to calculate the minimum value, as we are going to say that in that function, in that formulae, we are going to calculate the minimum value, right? So minimum value we are going to perform by this conditional statement. So this is going to be done for how many times? For R times, because for when my the first iteration, this R will be equal to 0 comma 1, and the second iteration the value of my R is going to become my 0 1, and then and it is going to become my R is equal to 0 comma 1 comma 2 comma 3. It means that now we are going to calculate the minimum element, and we are going to keep them into that matrix, and at the end what we are going to send, we are going to send the rightmost element of that matrix into that calling function, and now we are going to assume that that element, okay, that element which we are going to find there is the minimum cost of your optimal binary search tree which is being created. Okay, so this is the logic, very simple logic which we are going to follow whenever I would like to develop an optimal binary search tree for a given elements. So when I talk about the complexity, of finding your optimal binary search tree, this is order of n cube. The complexity of finding the optimal binary search tree will be order of n cube, because we have the loop of I, we are going to have a loop of j, and then we are going to have a loop of r. So we are going to have these three loops. And for these three loops, we are going to have n number of operations we are going to perform. So n into n, it is going to become order of n cube. So the complexity of the algorithm which is used for finding, which is used for calculating the optimal value is order of n cube. So this is a very simple logic by which we are going to design the program for your optimal binary search tree. So along with this code, we are planning to have more explanations along with the code, so that the student community is going to understand how the concepts are to be converted into coding. This will help them while attending their interviews, when they face the interviews, and where these people are asked to be code something there. And this type of coding will be helping the people.